Picking up where we left off last class, we were about to enter into section 6.4. 6.4 is all about what's called improper integrals. And there are two different types of improper integrals, where one of the limits or both of the limits of integrations are infinite, or there's an infinite discontinuity in the interval. So what does this look like? Well, there's two different ways to picture this. The first type of improper integral would be the kind where we're trying to find the area of something like this. So we go to negative infinity to infinity. The second type is far more familiar. It's the type where we try to integrate across something that goes to infinity and or negative infinity. These are two examples of these improper integrals. This first one, we're integrating from negative infinity to infinity. And the second one, we're integrating across an area where a function goes to infinity. So, two more examples of that first type. Like I said, in the case of a bell curve, integrating from negative infinity to infinity, or in this first case up here, integrating from 0 to infinity. So, what do these improper integrals look like? Well, there's three different types, right, for that first case. So that first case, we have the type where our upper bound is infinity, our lower bound is infinity, or both are infinity. So what I am saying is case one is from, say, a to infinity of f of x dx. Case two is from a, or from negative infinity to a of our function. And then case three is infinity and negative infinity. And the way we handle these cases to turn them into proper integrals and then solve everything is we start by rewriting them. In this first case, we're going to replace infinity with c and take the limit as c goes to infinity. In this second case, we're going to do the same thing, except now it's going to be negative c is going to infinity. There's a couple different ways to handle this third case. We can break it up and combine these first two cases, or we can take the limit as c goes to infinity with bounds negative c and c f of x dx. So their point here is just to notice that you can break up this integral from negative infinity to infinity into two subintegrals and treat those two subintegrals as the first two cases. But if we're going to do that, then it reduces to this here, right? Because once we treat them according to this, they're both going to have a shared limit, so we can bring them under one integral. Now there's an assumption here. Here we're assuming that our function is continuous within the intervals a to negative infinity, a to infinity, right? If these limits, after we do the entire calculation and apply the limit, if it gives us a finite number, we say that the improper integral converges to an answer. But if it comes out as infinity or negative infinity or does not exist, then we say that that improper integral diverges. So converge means you get an answer, diverge is everything else. I should say converge is you get an answer not equal to infinity or negative infinity, and then diverge is everything else. So, as an example, let's consider integrating 1 over x. Here, we need to rewrite our integral as the limit as c approaches infinity of the integral from 1 to c, 1 over x dx, well, 1 over x dx integrated, this thing's going to come out to be the limit as c approaches infinity of the ln of x from 1 to c, which is going to be the limit as c goes to infinity of the ln of c minus the ln of 1 What's the ln of 1? It's just going to be 0, right? Another way we can see that is by applying our properties of ln's or of logarithms. We know log base whatever of x minus y of x minus log base whatever of y is equal to log base whatever of x over y. So we could also look at this that way to find that this whole thing is just equal to the ln of c. Make sense what I mean? Folks at home, does that make sense?
Yes.
Awesome.
Yes.
Cool. So after we do that, or after we observe that, this is going to come out to be the limit as c goes to infinity of the ln of c, which is equal to infinity. So we would say that this integral diverges. Now they go about this slightly different because they use b instead of c, but the process is the exact same, right? And they determine the same exact thing, that it does in fact diverge. So we can think of this idea of convergence and divergence as, do we come to an answer or do we go to not an answer? Do we diverge from an answer or do we converge onto an answer? Another example let me write this on the board. Another example would be the integral from negative infinity to 0 of 1 minus 2x raised to the negative 3 over 2 power. This is, of course, equal to the integral from negative c to 0 of 1 minus 2x raised to the negative 3 over 2 power dx. Now, the first thing we need to do is apply u substitution here, right? So setting u equal to 1 minus 2x, du would be equal to negative 2 dx. So this tells us that our integral can be rewritten using u sub as the limit as c goes to infinity. I'm going to hold off on that actually. Yeah, I am going to hold off on writing out that integral because something happens here. I'm going to jump to the next slide to show what happens. They don't show it here either. They leave everything the same because they don't actually do U sub. Okay, so we need to put a placeholder in for these bounds because the second we use U substitution, things change. Our boundaries change here. So that is something we have to keep in mind. What they're going to say is compute the integral and then reapply your bounds. Make sense what I mean? But what we really need to do is say, all right, hold on. This thing is no longer C. This thing is no longer 0 because that was based off of X. Now we're integrating with respect to U. So when X was equal to negative C, this thing changes. This changes and this changes. Make sense what I mean? So we have to address that within our bounds. One way we can do that is by just doing the U substitution and bringing our bounds outside. So we know to integrate like we normally would, and then reapply our bounds. Unfortunately, like I said, they don't actually tackle this point here. They just go ahead and calculate the integrand, which in the end gives us 1 minus 2x all to the negative 1/2 power. From here, we have 0 to a, so this first case, or this first value, I'm plugging in 0, limit as c goes to infinity of, we've got 1 minus 2 to the 0, times 0, I mean to say, all raised to the negative 1/2 power, minus 1 minus 2 times negative c, all to the 1/2 power, close our brackets. So this thing becomes 1. We end up with 1 minus 1 minus, I forgot the negative here, 1 over the square root of 1 minus 2 negative c. Make sense what I mean? We can actually see them work it out here. Having said that, they do something slightly different here. They take their limit to negative infinity, and they set their lower bound equal to a. Since I made our c negative here, we have to take the limit to infinity. Does that make sense to everybody? Folks at home?
Yes.
Okay. So just making a quick point, because we're subtracting that negative, we're going to end up with 1 plus 2 times c, all raised to the negative 1/2. And now when we take the limit to infinity, it's a little bit more obvious. This thing blows up to infinity. So we have 1 over infinity, that goes to 0. So it's 1 minus 0, we get 1. So this improper integral converges. It converges onto the value 1. Now, as another example, we've got the integral from 0 to infinity of 2x e to the negative x squared dx. We're obviously going to apply u sub here, right? Because we've got u and du down here. So this is going to be the limit as c goes to infinity of the integral 0 to c of 2x e to the negative x squared dx. This is going to come out to be the limit as c goes to infinity of negative e to the negative x squared from 0 to c, which is going to be equal to the limit as c goes to infinity of negative e to the 0th power minus, my mistake, I wrote that backwards. I apologize. E to the negative c, that quantity squared, minus negative e to the 0th power. So this should come out to be the limit as c goes to infinity of 1 minus e to the negative c squared. All I did was rearrange terms in that last line, right? Because this thing is negative 1. So it's just 1. This thing is just going to be negative e to the negative c squared. So I just rearranged, like I said, the terms. Now, before we make any mistakes, because a mistake is definitely going to happen here, let's rewrite this again. This is now the limit as c goes to infinity of 1 minus 1 over e c squared. We don't want to confuse this negative for being part of c. So let's go ahead and rewrite it. Well, this thing is just going to come out to be 1, right? Because when c goes off to infinity, our denominator goes off to infinity. When our denominator goes off to infinity, our fraction goes off to 0. So we have 1 minus 0 in that limit. Now, checking out the answer, first really quick, what we just calculated was the area underneath the function 2x e to the negative x squared. We found the area from 0 up to infinity. So something of infinite length has finite area. That's what we just found. Which is kind of counterintuitive, right? So, looking at the way they did this calculation, same idea. They said rewrite the improper integral as the limit of b going to infinity from 0 to b of the same old integrand. After you find the antiderivative, you apply the limits. First you apply the bounds, then you apply the limits. It comes out to be 1. But again, like I said, I just find this cool. Something of infinite length has finite area. That seems so counterintuitive, but it happens all the time in math. Something can also have infinite volume, finite surface area. Infinite surface area, and finite volume. There's all sorts of weird, cool things that can happen in math. So, there was another issue with discontinuities. We have that second case, or that second type of improper integrals. I gave the example of 1 over x. Let me give another example. This is f of x equal to x to the negative second power. And if we wanted to find the area, say from -1 to 2, we'd have to find the area into 2 parts. First, the left-hand part, and then the right-hand part. And the reason why is because there's a discontinuity. So we have to break up our function into 2 different parts. We've seen this with like piecewise examples of absolute value signs. It's the same idea that we're going to have to do here. So I'm going to draw this again. Now I'm going to give a slightly different example. This is f of x equal to 1 over x. Let's say we wanted to find the area from 0 to 1. And let's say we also wanted to find the area from 0 to -2. Then in the first case, our integral would look something like this, right? But our function doesn't exist as 0. So we have to consider it in terms of the limit. So we would rewrite it as the limit as c goes to 0 from the left of -2 to c 1 over x dx. So that's this area right here. Now, in the second case, we would have from 0 to 1 of 1 over x dx. But again, our function doesn't exist at 0, so we have to consider the limit. We would say the limit as c approaches 0 from the right. Now notice, if we wanted to take the integral from -2 to 1, we would just break it up as these two different integrals, right? And add them back together. That is what they're saying here. So if your function is discontinuous at your boundaries, you have to consider one of these two cases. And if it is discontinuous inside, then you have to break it up into those two cases. Is everybody cool with that?
Yes.
Awesome. So, in this first example, we have a discontinuity at a boundary point. This first example is the integral from 1 to 2 of x minus 1 to the negative 1/3 dx. We're discontinuous at x equal to 1. So we have to rewrite this. This is the limit as c approaches 1. We're coming from the right because our interval is to the right of 1. So our limit has to be from the right. Of the integral from c to 2, x minus 1 raised to the negative 1/3 dx. So from here, we would calculate that antiderivative. The limit as c goes to 1 from the right of 2c, and I am not doing that in my head, so I'm going to cheat and look at the board. X minus 1 raised to the 2/3. So from here, we just apply the limit. We'd say, all right, this thing comes out to be the limit as c goes to 1 from the right of, plugging in 2 first, we're going to have 3/2 times 2 minus 1 is just going to be 1, raised to the 2/3 is just going to still be 1, minus 3/2 c minus 1 raised to the 2/3. So this is going to come out to be the limit as c goes to 1 from the right of 3 over 2 minus 3 over 2 c minus 1 2/3. We could, of course, factor out that 3 over 2. But no matter what we do here, this thing goes to 0. So we have just 3 over 2 left over. So, as one more example, the integral from 1 to 2 of 2 over x squared minus 2x dx. First thing you want to do is factor out the x and then apply partial fractions. At the end of these slides, there is a section on partial fractions if you don't remember how to apply them. So we want to apply partial fractions, break up our integrals, and then apply it accordingly. And then apply those rules. Having said that, we don't necessarily have to use partial fractions. We're only using it so that we can break up our integration into 2 other integrals. This one we don't have to worry about. This one we will. So jumping to the next slide, we have one more example. This one is x to the negative third. We're integrating from -1 to 2. Well, at 0, x to the negative third is discontinuous. So we have to break this up into 2 different intervals. One from -1 to 0 and the other from 0 to 2, right? But again, we're discontinuous, so we have to apply these limits now. So after we break up our integration, we can apply those limits. Do the integration, or rewrite it rather in terms of those limits. Do the integration, apply the limits, get our result. Everybody cool with this?
Yeah.
Awesome. So to answer the question, why do we do this? Why do we care? One place this shows up is in probability theory and statistics. When we start talking about the bell curve and the probability of certain events happening, what we're doing is we're looking at the relative area under a bell curve. Under a bell curve, from -infinity to infinity, the area should be 1. So if we took a fraction of that, that would be the percentage of a thing happening. And for that reason, when we apply it to probability theory, we can use integrations to actually find out how likely something is or isn't going to happen. So in our last section, we had talked about this idea of present value. One question a person might ask is what happens to the cost or the value of a thing if time were allowed to run out to infinity? And this would let you answer that question. That is the present value of perpetuity when time goes to infinity. And the solution to that would be to first start off by rewriting your improper integral in terms of limits, doing the antiderivative, or finding the antiderivative rather, Then breaking it up using partial fractions in the fundamental theorem. Partial fractions just may come up. You may not see it, you may see it. It depends on what that P is, right? So remember, present value is written in terms of a cost function. So depending upon what that cost function is, you may have to later down the road apply what are called partial fractions. But in any event, moving from the antiderivative on, you would just apply those bounds, evaluate the limit, and rewrite your answer in the most simple form possible. So, in the event that payments are constant, so in the event that CT is just a constant function, what the present value in perpetuity comes out to be is that constant function divided by R. So in the event of like an annuity, where again, it's a constant function. So all of this written in a nice, neat, compact form, everything I just said. Assuming your cost function is just a constant value, then the present value is P times the integral from 0 to infinity of e raised to the negative RT integrated with respect to t. This thing just comes out to be, in the end, P over R. I think, yeah, that's what I wanted, yep. And then just for completion, there is a quick example at the very end of how this would apply. The whole point is you don't necessarily have to do that integram or that integration. If you know P and R and P is constant, you already know what the solution is going to be. It's just P over R. So having said that, there is, at the very end of all of this, an extra section on partial fractions for anyone who needs to review those. They are very useful tools. They let us rewrite fractions like this. We could imagine a case where we get something much uglier than even that and need to break up our fractions in multiple parts. Say maybe it's the ln in your numerator. So maybe you have something like maybe this is what your fraction looks like. Using partial fractions, you can break it up into two different parts and potentially solve this in a much more easy way. Is everybody cool with that? Yeah, cool. All right. So having said that, I will let y'all go.